Good morning, guys. In this video, we are going to be doing a dimensional analysis of a pipe. Specifically, we're going to be making a dimensional matrix. And what we're going to do is say that if you had a null basis vector, or if you just had inserted any value into this system, you would be able to determine what dimensionless properties you have in your system. For example, you may have a Reynolds number, you may have length over diameter. You may have some other property that is dimensionless. And the whole point of this equation is that you would be able to sub in any value to achieve that. So by doing this first, what we're going to do is go ahead and make a Buckingham analysis of the properties that I've just described. So it says we have a pipe that is described by pressure drop, length, diameter, density, viscosity, and velocity. So what I have done is written down all of these properties and put them to the powers of certain letters. These can be any powers, but for this case, for the Buckingham analysis, what we're going, or for dimensional matrix, we're just going to assume that these are variables to solve so that when we sub them in, we can get any dimensionless, no, sorry, yes, any dimensionless group. So I already have the Buckingham chart here, so we're just going to kind of go through this mass, length, time diagram and kind of figure out what properties these have. So pressure is usually, let's see, this would be meter per length times some time squared. So this is going to be 1, -1, -2. For the length, this will be just 1 in the length, 0 in mass, 0 in time. Same thing for diameter, it's the same property. For pressure, that's going to be 1 mass minus 3 length. For the velocity, that is meters a second, so that's going to be 1, -1. And then viscosity, that is mass per length per time. So now what we're going to do is go ahead and make a quick matrix. I'm just going to make the matrix A in this case. And we're going to do it for the mass first, which we know this is 1, 0, 0, 1, 1. Do one of these, did I do one of these wrong? Oh, I'm sorry. Velocity is length, not mass. Thought that was wrong. 0, 1. Okay. Now we're going to do the same thing for length. We have -1, 1, 1, -3, 1, -1. And then for time, we have -2, 0, 0, 0, -1, -1. So we have to make our second matrix in this case. And this is going to go back to inserting the null values, the powers that we have to each of these groups. So we're going to say that I'm going to make a separate matrix. This is going to be X. And all this is just the powers that we have for our respective units. F. And essentially what we're trying to say is that when we combine these two matrices, regardless of what powers or what we have substituted in there, we want to say that our matrices together have some value that equals 0 in this case. So how do we do that? The easiest way to do that, in my opinion, is by looking at the Buckingham analysis and saying, how many units do I actually need to solve any other unit? In this case, we actually have a method for this. If we say n equals the total amount of units that we have here, so 1, 2, 3, 4, 5, 6, we have 6, and then we can subtract this uh, by the amount of units that we're observing per unit. So we have mass, length, and time. So this is 1, 2, and 3. So this is going to be -3. So we only need 3 known units in this case. So if we sub that idea back into here, we can actually make a pretty good matrix. So A of X, uh, yeah, we can make A of X equal, and we're just going to sub in all the values of A, B, and so on into this. So if we go into the first column, we have A plus ABD plus F. That is the first group that we have. Right, so I'm not crazy. Yep. And this equals 0. For the second group, we have negative A plus B plus C minus 3D, and this would be plus E minus F. And then lastly, we have the third group, which is negative 2A minus E minus F. And all of these equal 0. So now what we can do is go ahead. We only need to solve for 3 of these. So what I'm going to do is make equations for, let's say 3 of the equations here. Yep, I'm going to make equations for 3 variables such that we can get 3 known variables and just kind of sub them out in this case. So let's go ahead and start with the D. We can say D equals negative F minus A. And we can do something pretty easy down here too. We can say that E equals, if we shift F in 2A, that becomes positive, but we have to flip it because it's negative. So this is negative 2A, negative F. And if I insert these into the big equation over here, I get something like negative A plus B plus C minus 3. I'm going to sub in the equation here. Negative F, negative A. And then I have plus E minus, oh wait, sorry. This is plus negative 2A minus F, and then this is minus F. All of this equals 0. So I'm going to go ahead, just make sure I'm doing this slow. I'm going to go a little slower with algebra sometimes. This is plus 3F, and this is plus 3A. This is negative 2A, negative F. So let's go about this. I'll start with A. So we have negative A, that turns that into 2. We have 2A. So those two cancel out, so we don't have A. I have B by itself. I have C by itself. Let's see here. C by itself. If we go to E, we don't have E. Just making sure I'm going about this really slow. We have 3F. And we have minus F and minus F. So that turns us to 2F. That turns us into just F. But it should be plus F now. And I believe that's it. And I think B equals negative C, negative F. I am pretty sure. Again, I have to do this pretty slow just because I'm not super confident in my algebra all the time. Okay, so now we have these substituted values for D, E, and B now. So now what we can do is I'm going to go ahead and lasso all of this really quick. I'm just going to make this a little smaller. Okay. So now what we can do is make a matrix. And sub, it's going to be the same one as x over here, but now we have the substituted value. So this would be a b now equals negative c negative f, c equals c, d equals negative f minus a, e equals negative 2a minus f, and then f equals f. So this is our new matrix at this point with the substituted values that we had calculated. And now what we can do is begin summing in values. I'm going to go ahead and try to find all these dimensionless properties up here. So let's go ahead and start simple. I'm going to go ahead and let's go ahead and sub in C. Or I should, sorry, that's actually incorrect verbiage. I meant to say C equals 1. Let's do something like that. If we do that, our matrix ends up being 0, negative 1, 1, 0, 0, 0. So if we go back up here, B was length and D was diameter. So this is diameter over length. And remember, what's really nice about Buckingham is that if it's dimensionless, it makes no difference if you flip the reciprocal in this case. So we can actually just say that this equals length over diameter. And that gives us our first desired dimensionless property. So let's go ahead and proceed. Um, let's go ahead and say, hmm, what would prob? I'm gonna go ahead and try to get the pressure drop next. I'm gonna try to preserve value. Let's go ahead and say A equals 1. I think that'll get us what we want. If we do A of 1, this becomes 1, 0, 0, negative 1, negative 2, and then 0. So when we do this, we get change of pressure, and then this is D and E over pressure, and E is velocity. That is velocity squared. And that is our second dimensionless property. Pretty cool. All right. I'm going to go ahead and section this part off. So the next property is going to be when we make f equal 1. That's going to be our final substitution here. So when that happens, we get, let's try and make this look right. If we sub in f, we get 0. This becomes negative 1. This becomes 0. That becomes negative 1. That becomes negative 1. And that becomes 1. Okay, so lots happening here, but let's make sure we're going slow. We have viscosity in the numerator, and then we have length, and let's see, D is pressure, and then this is velocity. Okay, so something you may have noticed is that when we look at this, this does not look right. We have length instead of diameter, and our reciprocal is flipped in this case. So how do we fix that in this case? This isn't the dimensionless property that we want. Well, what's nice, another nice thing about dimensionless numbers is that if you do linear combinations of other dimensionless groups, what you can do is eventually just get your same dimensionless product as long as your units cancel out in this case. So what does that mean? Well, what I can do is take our dimensionals property that we solved for over here and multiply by L over D, and this would give us mu over D rho pressure uh, and velocity. And now if we flip the reciprocal here, we get pressure, velocity, diameter over viscosity, which if you look was the Reynolds number that we were trying to solve for. So this is called linear combination. And in a coding world, you'd be able to kind of just assert any value, like you'd be able to insert any numerical value and get whatever dimensionless property that you need from this. But this is what the actual math looks like if you were to do it yourself. But yeah, that is how you would get dimensionless groups with a null space and linear combination.